In this video, we'll look at lateral tire models. First of all, what do we need tire models for? Well, the purpose of tire models is to determine the forces and moments that act on the vehicle via its tire road contact. Clearly, the forces and moments which the tires exert on a vehicle are essential for the dynamics of a vehicle. Moreover, these are the only forces and moments that can actively be controlled, meaning by the engine and brakes of the system or the steering system. To look at this in a little more detail, consider this wheel of a vehicle. Now, via the contact between the tire and the road, in the contact patches, so-called tire forces and tire moments are acting on the tire. And that obviously holds for each tire of the vehicle. So the three tire forces or tire force components are split up according to the wheel's coordinate system. So first of all, we have the vertical force Fz pointing in the z direction of the wheel coordinate system. Then we have the longitudinal force pointing in the x direction of the wheel coordinate system and the lateral force pointing in the y direction of the wheel coordinate system. Correspondingly, of course, we have three moments. First, the aligning torque. Second, the overturning moment, and third, the rolling resistance moment. However, only one of them, the aligning torque, is really of importance, hence we will not consider the overturning moment and the rolling resistance moment in the following. For this section on lateral tire models, we make the fundamental assumption that the longitudinal force Fx is zero, or in other words, we have no acceleration and braking of any of the wheels. Later on in this course, we'll also look at longitudinal tire models where we neglect the lateral force, and finally at combined tire models where we consider both the longitudinal and the lateral forces. Before we start to look at concrete tire models, let's point out some of the difficulties of that discipline. First, the tire forces and moments clearly do not act on a single point of the wheel as in the diagram up here. Rather, they are distributed as pressures throughout the contact patch between the tire and the road. And as one can easily imagine, the distribution of these pressures in the contact patch is generally very uneven. Reasons for this are the relative complexity of the tire construction itself, including the tire tread, and also simply the fact that the road surface is not flat, but it's uneven by itself. The second difficulty is due to the complexity of the tire road contact on a very small contact patch. This fact is illustrated in a little diagram where we see a little rubber patch of the tire, and we see that at some points it has a close connection and adhesion to the asphalt of the tire, whereas at other points there is no contact between the rubber and the asphalt. And a third and quite obvious difficulty is that there can be different road and tire conditions. So for instance, the road can be wet or dry, there can be dirt on the road, the tires may have different temperatures, and so on. Despite of all those difficulties, or probably rather because of all those difficulties, a vast number of tire models have been proposed in the literature. Hence, it is impossible and it doesn't make any practical sense to try to list all of them. Instead, in this course, we'll look at a few particular examples to give you an impression of what tire models are and also for you to know about the most important ones. We'll start by looking at analytical models because they are relatively simple and easy to understand, and hence they provide a pretty good insight into the basic behavior of a tire. So the main idea of analytic tire models is to derive the tire forces from first principles in mechanics. To this end, what's needed is a friction law, such as the Coulomb friction, and a model for the elastic deformation of the tire. Here, the friction law is used to model the contact between the tire and the road, and the elastic deformation law is used to model the deformation of the tire between the contact patch at the road and the rigid rim which is attached to the vehicle. This elastic deformation is just represented qualitatively by these little springs in the diagram here. In reality, of course, these are not linear springs, but these are nonlinear elasticity laws, and also the whole elastic deformation becomes nonlinear due to the entire geometry of the tire. To make just a simple example of this nonlinear geometry, the size of the contact patch grows nonlinearly with the difference between the tire radius and the tire effective radius. Hence, assuming a constant pressure in the tire, the vertical deflection of the tire will vary nonlinearly with the vertical load on the tire. I assume that all of you are familiar with the Coulomb friction law from basic mechanics. Just to briefly remind you, in this little diagram, we see a sketch of the friction force depending on the relative motion between the two bodies. Note that the Coulomb friction law, which is also known as dry friction, splits into two parts. First, the static friction, where we have basically adhesion between the two bodies, and the dynamic friction, which is shown in blue here, which is if the relative motion between the bodies is non-zero. What this red line indicates is that in the static situation, the friction force can assume any value between a minimum value and a maximum value, which keeps the body in the static position. And only if this minimum or maximum static friction force is exceeded will move into the dynamic range of the Coulomb friction law. The tire model we're going to look at next is the elastic foundation model for lateral tire forces that has originally been developed by Ernst Fiala, an Austrian engineer, in his dissertation in 1954. The main idea of Fiala was to look at the deformation of the center line of the tire over the contact patch. So suppose this white rectangle represents the tire with the leading edge to the left and the trailing edge to the right, and in red we see the tire center line. Then we have a deformation of the center line over the contact patch, shown in green, and we assume the center line consists of many little tire elements which are connected to the undeformed center line via little springs, which are indicated in white here. If we now look at the center point of this contact patch, the spring forces will generate a lateral force in the center point, and also they will lead to an aligning torque around the center point. In the simplest case that one can imagine, we may just allow for a discontinuous displacement of the center line of the tire, and also for a discontinuous slope. This situation is sketched in the figure down here. We see in blue the wheel velocity, which is at an angle alpha to the geometric orientation of the wheel. So alpha represents the tire slip angle. And now the assumption is that the center line in the contact patch deforms along with the wheel velocity. And correspondingly, we get this dashed shape for the deformed contact patch. Clearly, in this situation, the deformed center line is discontinuous, and also the slope of the center line is discontinuous. So if you want to make this model more realistic, you may want to ask for the displaced center line to be continuous, and also the slope of this displaced center line to be continuous. However, we continue with our assumptions of a discontinuous displacement and discontinuous slope, and we'll now look at two cases. And the first case is where the slip angle alpha is so small that the maximum static friction force is not exceeded anywhere in the contact patch. Recall that this maximum static friction force is given as mu times the vertical force on the tire, where mu is the static friction parameter of the Coulomb friction law. To make this more specific, let's introduce a coordinate system in the contact patch. This is shown here in yellow. The x-axis runs along the undeformed tire center line, and the y-axis represents the lateral displacement of the center line. If C now represents the lateral stiffness of the tire, the assumption of a small slip angle alpha amounts to the condition that over the length of the contact patch, the lateral displacement is nowhere larger than the quantity mu times Fz divided by C. Note that we have defined the length of the contact patch to be equal to 2a, so the center point of the contact patch is at the coordinate x equal to a. Based on this, we can calculate the lateral tire force by integrating over the product of the stiffness and the lateral displacement of the tire over the entire contact patch and normalizing by the length of the contact patch. In our simple case, we have assumed that the lateral stiffness C of x does not depend on x, but is just a constant value, and the displacement y of x in our case is given by x times the tangent of alpha. So we get this expression, and if we perform the integration, we get the result CA tangent of alpha. Or with the approximation of tangent of alpha equal to alpha for small angles alpha, we get the lateral tire force is approximately equal to CA times alpha. So what we have obtained here is actually our first tire model, where the lateral tire force is proportional to the slip angle of the wheel alpha. The proportional coefficient CA is combined into a single constant, which is called the cornering stiffness, and it usually carries the symbol C alpha. And for this simple linear relationship between the lateral tire force and the slip angle, this tire model is also called the linear tire model. It's the simplest known tire model. However, it's very important in practice, probably exactly because it is so simple. Now let's also compute the aligning torque in the contact patch, for which we have to multiply C of x, y of x with the lever arm x minus a, and again perform the integration from x equal to 0 to x equal to 2a. And if we carry out this integration and again make a small angle approximation for the slip angle alpha, we get this expression where we again see that the aligning torque mz is given by a linear multiple of the slip angle alpha. Let's proceed to the second case where the slip angle alpha is large enough such that the maximum static force is exceeded at least some place in the contact patch. Looking at this situation in our little diagram, this means that the slip angle alpha has become so large that the direction of the wheel velocity is such that the displacement of the center line reaches its maximum value within the contact patch. The reason why the lateral force saturates in this part of the contact patch is not due to the lateral stiffness, but it's due to the fact that here the tire loses connection to the ground. And that's because the static friction limit in this part is exceeded. In other words, we have dynamic friction in this part. However, we assume that the static and dynamic friction coefficient is the same and it's given by this value of mu. Hence, the displacement of the tire center line in this case is given by y of x equal to x times the tangent of alpha for all x between 0 and x bar, and y of x equal to mu fc divided by c for all x between x bar and 2a. Note that in the first case we still have static friction, whereas in the second case we now have dynamic friction. Observe that the value of x bar is defined by the condition that x bar tangent alpha equals to mu fc divided by c. So this formula here, which we can solve for x bar equal to mu fc divided by c times tangent alpha. Now computing the lateral tire force in this case, the integral over the center line of the contact patch splits up into two integrals, one going from x equals 0 to x bar and including the first y of x, and the second integral going from x equal to x bar to 2a with the second y of x. And if we calculate the values of these integrals, we get this result, which holds if alpha is greater than or equal to mu fc divided by 2ac. And this in turn comes from the fact that alpha has to be large enough such that the displacement has at least this form. So in other words, we have to substitute 2a for x bar here. And then we do again a small angle approximation for the tangent to get to this formula. What's interesting about this formula for the lateral tire force is that it does not depend linearly on the vertical force. Instead, for a fixed value of the slip angle alpha, we get that Fy increases less than proportionally with Fz, and we kind of have this quadratic formula here. And this effect is something that we actually see in empirical tire data that we will get to shortly. For the sake of completeness, we also state the formula for the aligning torque mz down here. Okay, now we got to know a basic but very important analytical tire model. I've already mentioned that there are, of course, many more tire models with more difficult and complex assumptions and calculations. And that's, of course, because tire models are so fundamentally important for the dynamics of a vehicle. In the most extreme case, so for professional vehicle simulation packages, Analytical tire models consist of finite element models, so they contain up to thousands or even millions of states, just to provide a realistic description of the tire road contact. The second large class of tire models, besides analytical tire models, are empirical tire models. The main idea of empirical tire models is to choose a certain class of functions that contains parameters and then to fit those parameters to the measured data of the tire from a tire test bench. In a tire test bench, a given tire can be tested under all imaginable conditions, and there are integrated sensors that measure the speeds of the tire and also all forces and moments acting on the tire. Looking at many of these empirical data sets for different tires and under different conditions, the lateral tire force Fy roughly behaves as follows. First, we look at the behavior of the lateral tire force depending on the slip angle alpha. And from this yellow curve, for a fixed vertical tire force Fc bar, we see that for small values of the slip angle, the tire force depends almost linearly on the slip angle. So in other words, there's a small interval around the origin in which the linear tire model that we have seen before is a very good approximation to the data that's observed in reality. The slope of this linear approximation is called the cornering stiffness, C alpha, of the nonlinear tire model. If we increase the slip angle further away from the linear interval, and by the way, the curve is symmetric, so it doesn't matter whether I do this on the right side or on the left side, then we see that the nonlinear behavior of the tire kicks in and the lateral tire force reaches a maximum peak, so that if the slip angle increases further, actually the tire force is reduced. The deviation of the actual tire force in yellow and the ideal linear behavior of the tire is also called the saturation of the tire. More specifically, the saturation level alpha sat for a given point on the nonlinear curve is defined as the difference between the actual slip angle alpha and the slip angle that would be necessary to generate the lateral tire force if the tire behavior was entirely linear. So it's this difference between the linear line and the line on the nonlinear curve. The precise shape of the yellow curve, including also the cornering stiffness, is influenced by many variables in practice. So for example, it depends on the tire size, on the construction type, so radial ply versus bias ply construction, the number of plies that are used and their angles, and the general tire and tread design. A very important variable is, of course, the aspect ratio of the tire. The smaller the aspect ratio, the more stiff the tire will be. For any given tire, the main factors are the inflation pressure of the tire and the load on the tire given by the vertical force Fz. In particular, this last point is worth looking at a little more closely because with the roll and pitch dynamics of the vehicle, the vertical force of each tire also changes over time. Generally speaking, of course, the lateral force will increase if we increase the vertical force, and it will decrease if we decrease the vertical force. Often, also the cornering stiffness, so the slope of the yellow curve, increases if the vertical force is increased and decreases if the vertical force is decreased. It may happen that this peak here is more prominent for smaller loads on the tire, and it's much smaller or maybe even non-existent for higher loads on the tire. It is a popular assumption that this curve scales proportionally with the vertical load Fc. So in other words, for the quotient of Fy and Fz, we can just use the same curve. Often, this is actually not a bad assumption. However, in reality, it's not entirely true. Actually, for a constant slip angle alpha, the dependence of the lateral tire force on the vertical load looks more like a parabola with a negative quadratic term. So in other words, the lateral tire force increases less than proportionally with the vertical load. Okay, now that we have a rough idea of how tires behave in reality, let's look at the most important empirical tire model, the Pacejka tire model. So the Pacejka tire model is by far the most commonly used empirical tire model in practice. It is named after its inventor, Hans Pacejka, who was a Dutch engineer and a professor at the Delft University of Technology. The model is based on the magic formula, which is this expression that gives the lateral tire force in dependence on the slip angle, alpha, the tire road friction coefficient, the vertical tire force Fz, and a total of 4 constants B, C, D, and E. This formula cannot be derived from any first principles or anything, and that's why it's called the magic formula. It just has proven to be a very good approximation in many practical situations. In order to use the Pacejka tire model, of course, we have to fit the parameters of the magic formula for a particular tire. And to this end, we collect a bunch of empirical data points, which you see in red here, for the slip angle alpha and the ratio between the lateral tire force and the vertical tire force. And then we fit our model parameters B, C, D, and E so that the magic formula curve fits as good as possible to the empirical data points. This fitting process, of course, requires a little bit of experience. And in practice, there are a few more parameters than just our parameters B, C, D, and E. So for example, offsets. Roughly, one can say that the stiffness factor B is used to control the slope of the magic formula around the origin. The shape factor C controls the location of the peak along the alpha axis. The peak value D controls the height of the peak. And finally, the curvature factor E controls the shape of this peak. Of course, there are many extensions to the Pacejka tire model, and if you enter this field professionally, it becomes a science in its own right. However, for our purposes, this level of detail shall be sufficient. So we now have a good grasp of what tire models are and what they're used for, and we've also seen the most important tire models, except for Dugov's model, which we will consider later on.